atomic mass of chlorine is equals to 3 times 35 plus 1 times 37 all over 4, which will give us 35.5. Example 2. A. 94Be represent beryllium atom. Explain what the number 9 and 4 stands for. B. Chlorine is an element of atomic number 17 and atomic mass 35.46. It has naturally occurred isotopes of mass number 35 and 37. Calculate the relative abundance of the two isotopes. Solution. A. Neutrons plus proton equals to 9. 4 is equals to atomic number. 9 is equals to mass number or atomic mass. B. If the ratio of the number of atoms of isotope 35 to those of isotope is 37 is S, then the atomic mass is equals to 3 times 37 plus 1 times 37 all over S plus 1 equals to 35.x. Solving, we have that S is equals to 3. The relative abundance of the two isotopes is equals to 3:1. Size of molecules. The size of atoms and molecules can be estimated by allowing an oil drop to spread on water surface, and the molecule size of oil obtained should be a value of the order of 10 raised to power minus 7. Theory. The volume of oil equals to volume of film. 4 over 3 pi r raised to power 3 is equals to square root of r squared pi h. This will be our equation 1, where h is the height of oil film, which equals to the thickness of one molecule. R, small r and capital R are the radii of the oil drop and oil film respectively. We therefore have from equation 1 that h is equal to 4 over 3 pi r raised to power 3 all over pi capital R squared. This will be our equation 2. Thus, h, which is the thickness of one molecule, is obtained from above equation 2. Example 3. The following results were obtained from estimation of size of olive oil. Diameter of small drop on loop is equal to 0.05 cm. Diameter of oil film on water is equal to 20 cm. Calculate the length of one molecule of oil. Solution. Diameter of small drop on loop is equal to 0.05 cm. Therefore, radius of small drop on loop is equal to 0.025 cm. Therefore, volume of small drop of oil is equal to 4 over 3 times pi times r raised to power 3, which is equal to 4 over 3 times pi times 0.025 raised to power 3 cm cube. Diameter of oil film on water is equal to 20 cm. Therefore, radius of oil film on water is equal to 10 cm. Therefore, the volume of oil film on water is equal to 2 pi r squared h. Pi times 10 raised to power 2 times h. Volume F of film of oil is equal to volume of oil drop on loop. Pi times 10 raised to power 2 times h is equal to 4 over 3 times pi times 0.025 cube. H is equal to 4 times 0.025 cube all over 3 times 10 raised to power 2, which is equal to 0.000000002 cm, or 2 times 10 raised to power minus 7 cm. Therefore, the length or thickness h of one molecule of oil is equal to 2 times 10 raised to power minus 7 cm. 5.2 Elastic properties of solids. Hooke's law. Hooke's law states that the extension E produced in an elastic body is proportional to the applied force F, provided that the elastic limit is not exceeded. Force is equals to F is proportional to the extension E, or F is proportional to E. F is equals to Ke, where K is constant of spring or wire known as stiffness or elastic constant. If F is in Newton and E is in meter, K is equals to F over E in Newton per meter. Tensile stress, tensile strain, and Young modulus. Tensile stress is equals to force over area, which is equals to capital F over capital A. The SI unit of stress is Newton per meter square. Tensile strain. The tensile strain is extension E per unit length L. Tensile strain is equals to extension E over original length L is equals to E over L. Note, tensile strain has no unit since it is a ratio of two lengths. Young modulus. Young modulus, capital E, is defined as the ratio of tensile stress to tensile strain. Thus, capital E is equals to tensile stress over tensile strain is equals to F over A all over E over L. Equation 1, where F is equals to the force, A is equals to the area, E is equals to the extension, and L is equals to the original length. From equation 1, it follows that force F is F equals to capital A, E, small e over L. Equation 2. The SI unit for Young modulus E is Newton per meter square, and M is the power minus 2. Work done in springs and elastic strings. Work done is equal to force times distance. Work is equal to average force F times extension E, which is equal to half Ke squared. Using Hooke's law, F is equal to Ke. Therefore, energy stored is equal to half Ke times E is equal to half Ke squared. Energy stored is equal to half Fe, which is equal to half Ke squared. Example 1. If a string has a stiffness of 950 Newton per meter, what work will be done in extending the spring by 60 mm? Solution. Extension E F of the spring is equal to 60 mm, which is equal to 0.060 meters. Stiffness K of the spring is equal to 950 Newton per meter. Work done is equal to half Ke squared, which is equal to half times 950 times in bracket 0.060 squared, which gives us 1.71 joules. Example 2. A force of 10 Newton extends a spring of natural length of 1 meter by 0.02 meter. Calculate the length of the spring when the applied force is 40 Newton. Solution. Using Hooke's law, F is equal to Ke. Therefore, 10 is equal to K times 0.02. Therefore, 10 is equal to 10 over 0.02, which gives us 500 Newton per meter. Also, F is equal to Ke. Therefore, 40 is equal to 500 E. Therefore, E is equal to 40 over 500, which gives us 0.08 meters. Therefore, the length of the spring is equal to 1 plus 0.8 is equal to 1.08 meters. Example 3. If the extension of a spring when mass of 8 kg is attached at one end is 2.45 mm, calculate the work done in extending the spring. Solution. Work done is equal to half load times extension is equal to 1 over 2 Fe is equal to half times 8 times 10 times 0.00245 is equal to 9.8 times